Okay, so hello everyone. Today Jonathan is gonna be discussing some ideas about non-reciprocal phase transitions, but also on foundational models. And so the floor is all yours, Jonathan.
Okay, yeah, great. So I was just saying, I think some people have just joined, but I kind of had this vision of blending these two topics together. The phase transition paper describes a scenario where there's emergent phenomenon in natural systems, but also in models of natural systems. And that is something I want to talk about. And I think that is directly related to foundation models and how they work, but there's a lot to cover on the foundational model aspect of this talk, and I don't know if we're going to get super far into the emergent phenomenon stuff because at the workshop we did talk a lot about foundational modeling, and we wanted to cover a lot of that. And I've been discussing the foundation model topic with Chris and with Mayoa and with Andrew and a few others. And it seems like there's a really good interest to keep that topic at least relevant to this group. And we talked about some ideas of how to start maybe a program to get into that area of modeling. And so I'm going to probably spend most time talking about foundation models, but I do think that foundation model
Jonathan, we lost your sound.
Oh, we just him. Okay, let me email him.
It still says I can't share. I'm host has disabled screen sharing.
Hey, Jonathan, we missed you for the last couple of minutes.
Oh, really? Couple
Yes.
minutes?
Yes.
Oh, no.
Probably
Okay.
1 minute at least.
Okay. Okay. Can you enable screen sharing?
Oh, yeah, sure. Okay, you are the co-host now.
Okay. All right. Well, sorry about that. I guess what I was trying to say is that I think that the ideas in the phase transition paper, specifically that of emergent phenomena in natural systems and emergent phenomena in modeling, is related to foundational models and how they work and what we want to get out of them. But there's a lot I think that we want to cover with foundation models, and I think that's a topic that we've been really interested in since the workshop. So I'm going to focus on foundation models, and we'll see if we get into this idea of emergence for now. So let me, you can see my screen, right? I'm going to try and share.
Yes, we can see your screen. We are seeing.
Okay. Slideshow. Okay. It says loading. Okay. Sorry for the rocky introduction. All right, so I don't usually like to give outlines of the presentation, but because there's so many different things here, I thought it was important. So I am gonna give a little bit of an outline of what I'm gonna talk about. So I'm gonna talk about the characteristics of a foundational model and what specifically we want in a foundation model, and then why that is a topic that if you remember, for those of you that at the workshop, Gray Nearing proposed as like an important step forward for machine learning and information theory for modeling. And so I'm going to talk about why foundational model is an important next step. Then there's two good examples of foundational models for Earth system science. A project called ClimateX that's out of UCLA and Microsoft, and then there's a NASA IBM collaboration. It's a geospatial AI foundation model. So I'm going to go over some examples from those two projects. Then I am going to talk about some ideas that I've been talking for a while about with Gray and some other people about text-based foundation models versus data-based foundation models. So I see that it does say my internet connection is unstable. Am I still with you all? Yeah, okay. So hopefully this works out. And then we'll get in, if we have time, we'll get into some ideas of emergent behavior and why I think that this is something that is important for foundational models to work. And then also some interesting, I think interesting ideas I have about emergent behavior and modeling in general. So the idea behind a foundation model is that you use a lot of data in a really big model with some certain characteristics that allows you then to fine-tune a model to a system where you might not have so much data and you can get good results with lower amounts of data. So that is increasing the efficiency of learning on small data systems. So this is a paper about few-shot learners and specifically about language models being few-shot learners. So ChatGPT is a large language model that was trained on what will be referred to a little bit later as the internet scale of text data. So using a very large data set with a very large model. So on the right-hand side here, these lines are color-coded by the amount of parameters in the model itself. So in this example, they're training different size models. As you increase the parameters of the model, so the complexity of the models themselves, then what this shows is that when you fine-tune a model with some small amount of data, you're able to get better accuracy with it. So there's a couple of definitions here. Fine-tuning a model is when you're updating the weights of a pre-trained model with the new data. Few-shot learning, you're not actually updating the weights, but you're conditioning the model at the time of inference. So this is what ChatGPT does. When you type in your prompt and it's giving you a result based on your prompt, it's not updating the weights, it's just giving you, it's just conditioning the model based off of your prompt. So what this figure shows is that if you have a highly complex model, like 10 times, blue is 10 times what the orange line is, then when you are prompting your model with something, prompting something like a text model, you're able to get better accuracy. So this is the idea that we take a large data set with a very large model with a large number of parameters, we pre-trained, then we can use that model to either fine-tune or do few-shot learning. And so this is what the idea is in the foundational model approach. So this is this specifically is referencing text data, but the idea is the same if we're dealing with a data-based, an environmental data-based type of foundation model for Earth system science. A couple of key things about the foundational modeling approach that we discussed a lot at the workshop is that the foundation model, I don't know if it's necessary, but it's as far as I can tell, we need to be working with a generative model. So this means a model that is going to be not distinguishing between boundaries of data, but more a probabilistic approach. So not like a hard boundary between different types of data, but a probability distribution on data. So this allows the model to instead of trying to match a target directly, it allows the model to make a prediction that is in a good representation of the probability distribution. So this is something that I've been kind of thinking through a bit, and I think a good example of this, and this is why I think ChatGPT works so well, is that if you prompt a model that what color is the ocean, that model can give you the answer of blue. That's a really good answer. But depending on the context, green is also a really good answer, but every once in a while, red is the best answer. So red has to fall in that probability distribution at some point if you're going to talk about algal blooms. So one of the key things about generative AI is that there's not always a single right answer. It's that you're really dealing from the probability distribution. So if you're writing a sentence that is trying to describe the ocean, blue is not always the correct answer. So you can't always try to match a target exactly. So that's where the idea of self-supervised learning comes in, because if you're cycling through data, patterns are going to emerge where the most probable the most probable answer to a completion of self-supervised task is not always the correct answer. So generative AI is a necessary part of this. And then self-organization of data is what makes these foundation models work. So I was doing some literature review on self-organization of data, trying to look into exactly what that means from a technical standpoint. And this is an example from a paper from several years ago where they are doing a dimensionality reduction. But this paper is kind of a good starting point for thinking about self-organization of data, where what you want is a continuous map between one point in the model to another in a data space that crosses dimensionality of your model. There's a forward mapping from the input space and a backward mapping from the output space. So what ends up happening is if you have data that goes into your model, patterns emerge before the data comes out of the model. And it's those patterns that are emerging in the model itself that the model's weights learn to recognize, that allows a system where there's fewer data that you're training on, and you're fine-tuning those data, they're going to fall hopefully within these patterns. So the idea of self-organization of data is what is going to allow a foundation model to take a system where there's large amounts of data and allow us to take that trained model and be efficient on learning something new from a system of small amounts of data. So in this particular case, it's a dimensionality reduction model, but the idea, I believe, is the same for if we were using something like an attention network on a large amount of data to do self-supervision of one task, and then we train that same model on a secondary set of data. So self-organization is the key.
Can I ask a question, Jonathan?
Yes.
So in terms of self-organization, I mean, the closest I come to understanding that is from a long time ago. What they had was self-organizing feature maps, where they mapped the data into some lower dimensional space as a mesh of some kind. More recently, I can think of this as being something like a mapping into a lower dimensional latent vector space. Is that what we're talking about? Is there something special about this that I should understand?
Yeah, I think that's a good way to phrase it, because they're not actually reducing the dimensionality of the data themselves, but the weights of the model is what is organizing. So the weights of the model might include that dimensionality reduction, where there might be some pattern of weights where when you put in the new data, those weights are automatically transforming the data into these organized patterns. So is that, I think that's what you mean by the latent variable. Does that make sense?
I'll see as we go along. I'm just curious what's new about. I mean, in principle, it just seems to me that anytime you map into a latent space, you're doing some kind of dimensionality, possibly dimensionality change in organization, where you're mapping the data from whatever dimension space it is into some other space. In self-organizing feature maps, they were designed so that you could kind of map it down to 2 dimensions, and you could kind of understand what was going on in some dominant dimension space. And I kind of understand how that works. And I kind of understand how k-means algorithms kind of work. I was just curious if there was something different about this from simply just applying a neural network and mapping it into a latent vector space of some kind.
No, I don't think that there's anything necessarily new or different about this. The one thing is that I'm not entirely sure about this, but it's something about the way that the model weights are learning these organizing patterns. With new information, they will still fit into these organized patterns, whether or not they're from the original training set or not. So I don't have any real concrete technical answer for that question.
That's fine, thanks.
So then getting in a little bit into the motivation of the foundational model approach is that we have a lot of data that may or may not be being used completely. A lot of the data that we have might not be necessary for the specific tasks that those data are collected for. For instance, we'll see what happens with some of the newer satellites. But this, I was trying to look in. We talked a little bit about the amount of data that is collected from like Earth observing satellites versus the amount of data that is actually used from those Earth observing satellites, and the SWAT and NISAR programs alone generate 100 terabytes of daily data, and that's not the amount of data that is actually being used by those. So we're collecting, or we're measuring, I think, orders of magnitude of data more than what we're actually seeing when we're using those products. So if you have a measurement device that is measuring more points than you can reasonably represent in like either your map that you're producing, or you have to like do some averaging of those data or some processing of those data to reduce either the spatial resolution or the temporal resolution, or to convert the measurement into some aspect of a system that you understand. we're going to be losing a lot of the actual data that comes from those measurement devices. So, but the key is that we have hundreds of terabytes of data that come in daily, and we're not necessarily using all of those data. But the other thing is that those specific data are collected for a specific purpose, but it's not always the case that those data could only be used for that specific purpose. Go ahead, Hushin.
I'm just curious, because I don't work with these data sets, but are they stored in compressed format? I mean, we should be thinking in terms of how much information is being collected as opposed to data, right?
That's right. Yeah. So that's kind of what I was, I guess, trying to say without using those specific words. But yes, that's kind of what I'm getting at, is that we measure redundant information from our sensors, and then we compress them as best we can so that the user isn't using 100 terabytes of data per day, because that's not feasible. But we're trying to get out of that what somebody has thought of as the compressed information that individual is using, or that an individual might want to use for that specific purpose.
And
so
are we using generic compression to store those data, or is there some scientific information being used, process understanding to compress? I'm just curious because this relates to work that Stephen's done.
Yeah, all of the sensors, I don't know all of them, but most of them have their own levels of compression. So a lot of times they are putting in models of a physical phenomenon to compress that data into something that we understand. So if we're looking for a measurement of snow cover, but what a satellite is actually measuring isn't snow cover itself, but some electromagnetic signal that we then can map into a representation of snow cover, we are putting in something like process understanding or physical understanding into that data to compress it into the space that we want. And in doing so, we are necessarily we're likely losing some information that could be useful for some other Earth systems application. So a measurement that you might take specifically for snow cover might also be useful for something like an ecosystem application if you had the raw data, but maybe not the compressed data. And then a huge challenge that I think is going to be, I think the biggest challenge to a foundational model for Earth science is the fact that these data are they're heterogeneous, because most of these sensors go up for a specific purpose. They record data for a specific purpose, and they report data for a specific purpose. And those formats have different units, vocabularies, and structures that are meant for one purpose or another. So the atmospheric scientists that work with Earth observation data, they get their data in some format that's different than the ecosystem scientists. And so for a general Earth system science type foundation model, but figuring out a way to get homogeneous data into a single model is a huge hurdle. And we'll see that in the ClimaX example, a way that they went about that. And then I'm going to discuss a little bit about my idea of using text-based models instead of these data type based models. But I think that in general, this is like probably the biggest challenge that we have for going to the foundation model aspect of this. So this is an example that I always think about this, the fact that we are measuring from geostationary orbit the full Earth disk every 10 minutes from at least two angles on the North American continent, from the west and the east. And so when I was working with Floodbase, a lot of the problems that we always had was that there's not always a satellite measurement when we need it. And the coverage of that satellite measurement isn't always what we need. And that has to do a lot with clouds and everything. But one thing that we learned to do is use the context through large spatial images to get local information. And so I'm bringing up this idea of the GOES satellites as a specific data source that I think is underutilized in Earth systems modeling, because we're taking a picture of the Earth from geostationary orbit every 10 minutes from 2 different angles. And even though this doesn't have the specific information we might want for a specific modeling task, I think that the context from these types of images is rich enough that they can be transformed through this foundation model type of approach to get information that we want for many, many specific modeling tasks. So what I'm saying is that there's the big global phenomenon that goes across the Earth, I think can be better used for local specific phenomenon through that context. And like one specific example I always talk about is that if you have a storm that's coming from the east or a storm that's coming from the west that hits the same location, even if they dump the same amount of rainfall, they're going to behave differently. And that's not something you can get if you're just measuring rainfall across the entire basin. But if you have a time series of the storm leading up to and then through the event, you can get the information of the directionality of the storm. And so this is just an example of where I think we're leaving a lot of data on the table. And so we'll talk about some specific examples of foundation models, but I do think that there's an approach that can be used for taking these kinds of data, creating a foundation model that does the self-organizing of data, then using that foundation model to fine-tune for a specific application where the model will have understood in the weights at least some of the context that comes from these global scenarios. So then I think the last aspect
Jonathan?
Yeah.
Antoine has a question.
Oh, yeah.
Oh yeah, if you mind, can I just ask to rephrase that real quick, just to make sure I understood what you were saying? What you're saying is we can leverage that high resolution and high frequency data by using foundational models that would shift the dimension to something we could exploit. So that connects to what we were saying about emergent behaviors. Is that correct?
Yeah, that's what I'm. That's
Okay,
exactly
thank you.
right.
I was just trying to find out if I got this. Thank you.
Yeah, that's exactly right. So I wanted to have some quick definition of transfer learning, because this is something that is basically what allows the actual model itself to be used in this foundation model and fine-tuning approach, where so I just went to a textbook, and transfer learning deals with how systems can quickly adapt themselves to new situations, tasks, and environments. So adapting themselves to new situations, tasks, and environments is the key here. So we want to learn something from one big training exercise and then adapt to some specific exercise. Okay, so then there is, I think, a really important question is why we would even want to be going through a foundation model approach for Earth system science. And so Adam, you probably picked up I'm using Earth system science because we talked about this quite a bit, and I don't want to use like the phrase hydrology. I think that there's a lot of aspects of the Earth system that we can get from a single type of from a single model. So way beyond just hydrology, even though a lot of what we usually talk about is mostly hydrology and different types of hydrologic systems, groundwater systems, land surface processes, runoff processes. I think there's a whole suite of Earth systems that are all well connected enough that a single foundation model can be used for many different types of Earth systems. So why do we want to go after a foundation model? Is because so we can exploit the vast amount of data we build with built for purpose models. We also want to be able to tackle situations where data is actually limited. So I think in general, we have a glut of data that we are maybe not taking full advantage of, but then we still have some systems where we just do not have enough data to build a really good model, either a data-driven model or even understand the physical processes themselves. Water quality, I think, is a good example of that. So there's our water quality data sets are growing, but if you look at any specific catchment and you actually want to understand like where water quality issues are coming from, it's really hard to do that from the small amount of data that we can collect in any specific catchment. And that's because you can't always collect water quality data when it's most important. You can't continuously collect it, and it gets expensive to actually run the laboratory equipment to measure it. So there's another question. Go ahead.
Yeah. Hi, Jonathan. I've been wondering from the beginning, and I still don't know what's the difference between a foundation model and a model. So what is the foundation? What does it actually mean?
Yeah. So okay. The foundation is the pre-trained model. So we're training a model on some large amount of data, and that's a pre-trained model. But then we want to use that model for another purpose. So we either have to retrain it or we prompt it. So let me just go back here, and I guess maybe I can get to this. So if this is an example of 3 different pre-trained models with different numbers of parameters, one with only 1.3 billion parameters, 13 billion parameters, and 175 billion parameters. These are the foundation models. And then this curve represents the accuracy when you prompt the model with something during the time of inference. So you're using the foundation model not to give you the prediction of something that it was trained to give you, but you're prompting it to give you something else. So the foundation model is a model that is self-supervised and trained and creates this self-organization of data that then we take that pre-trained model, and then we can either train it through fine-tuning or a few shot. And hopefully that model allows us to have some new utility for it. And,
so basically we could have a huge amount of data on, let's say, soccer results, train our model on soccer, and ask our foundation model to predict hockey results.
Hockey results? Yeah, that's right. Yeah, so if the idea being that if the model starts to learn, okay, there's some sort of thing where there's a ball going into a net back and forth, people are trying to stop it. That whatever it learns on that system can be applied to hockey, because it's a similar type of thing where there's a puck now going back and forth and people are trying to stop it from going into a net. So it hasn't seen hockey, but it has learned something that can be directly applied to hockey.
Okay. Thanks a lot. That helps me a lot to put everything in context. Thanks.
I'm not sure this is complete, Jonathan, but that's sort of the term background knowledge comes to mind. Something that human beings we take for granted as we acquire over the course of our lifetimes.
Yeah, I totally agree. And I think this is I guess that I didn't explicitly say this, but the transfer learning approach is with the foundation model has to take advantage of this idea of transfer learning, where a model has learned something that can then be used to quickly learn something new. And the background knowledge, would be a really good anthropomorphic example of that, where somebody that has spent a lot of time studying math can then pick up physics a lot easier. Or somebody that has spent a lot of time learning about soccer can probably pick up the rules of hockey a lot easier versus somebody that has never played or seen a team sport before. Okay, so the one main motivation is trying to have a model that we can use on smaller sets of data. So the idea that training a model on small amounts of water quality data might not give you really good results that you can be generalized everywhere, but from a model that has seen a lot of stream flow dynamics and maybe earth system processes and land surface processes, maybe it has learned something about water quality that only from a few data points a model can then make good predictions of water quality, or be used for some aspect of water quality that you wouldn't be able to get from a water quality specific model. And that, I think one of the most important things here is that you want to be I think that most hydrologists tend to deal in systems where they have to analyze counterfactuals for design and decision making. So for instance, if you are building a new housing development in a small watershed that is 100% dealing with or 100% supplied with groundwater, and you want to know if the new housing development is going to draw too much groundwater from the system that the whole watershed itself can no longer sustain itself. So that's actually an example of a project that I'm working on right now, where we're analyzing a small watershed that is 100% relying on groundwater for its water resources, and there's a proposal to add a housing development. And what we need to do is analyze the water balance to see if there's a situation where like an extra couple of houses are going to be the straw that breaks the camel's back, that is going to make the groundwater unsustainable for everyone else that lives there. So what we have to do is go through a lot of counterfactuals of different use cases and different yields scenarios, and see at what point is adding a new housing development going to not allow everyone to have the water resources that they need. So this is the actual task that I guess most of the hydrologists that I've ever worked with tend to do. So there's the hydrologists that I've been working with in academia that build models just for making like accurate predictions. And then there's all the hydrologists that I've worked with in industry that are tasked with solving a problem, and the models are used to help them solve the problem. What they actually want to do is take those models and run different scenarios to see when some scenario might be good, one scenario might be bad, so that they can make a decision or design some infrastructure that will help supply water for some community or some state or entity like that. So analyzing counterfactuals is something that foundation models can do a lot better. And that's seen exactly if you think about ChatGPT, when you're prompting ChatGPT, what it's doing, it's running through all the data it's seen, and it's trying to figure out where your prompt fits into all of the data that it's seen. And it's not always fitting into the exact same place. So it's looking for different locations in the training data where your new scenario fits in. All right, so 2 recent examples of foundation models in Earth system science. So this is a paper that was presented at the HydroML conference in March this year in Berkeley. if you were there, hopefully you saw a little bit better of a presentation, but I'm just going to briefly go through it. Not being a total expert on it, but I did review this paper several times with the help of Chris, so thank you very much. This is a foundation model that is specifically for climate. So this group wanted to train a model on a large data set and then see if they can use that model trained on a large data set for different scenarios. Some of the scenarios that they are targeting are lead time. So if you train a model to make predictions at a 6-hour lead time, how good is that model making a prediction at a 6-day lead time? And then another type of scenario that they analyze is if you train it to make predictions on one variable, how good is it making a prediction on a completely new variable? So they bring up a couple of really important points in when they're describing this model. They want to know, is the foundation model approach going to be better in terms of accuracy than a built for purpose model? So is a general purpose model that has seen a large amount of data going to be better in accuracy than a built for purpose model? They refer to the scale of the data set. So they talk about the success of GPT and that has come from an internet scale data set where GTP has seen basically all of the text on the internet. And that massive amount of data is what has given it the ability to be so successful. And then there's an objective question where what is the objective that you actually want to train on, where that objective can be transferred to your new scenario. So the goal is that you want to have your model be able to have emergent capabilities that the model was not trained for. And we'll see that the model is trained on some types of variables here, and then they test it, fine-tuning it on other types of variables. So that the model is demonstrating an emergence of capabilities. There's a couple of modeling novelties that they employ here. One is, this is called variable tokenization, where each individual variable is put into the model such that the model sees all of the variables at once, but it knows that each variable that it sees has individual characteristics. This is a vision transformer. So this is the same type of model that something like the image generating models use, like DALL-E. So the transformer model is generally the model that's most used by foundation modeling approaches. They pre-train it on the Chimp-6 data set, and then they're trying to predict weather at different lead times. So then when they take that model that was trained on that specific
Can I just clarify? You're talking about this variable tokenization issue. Is that sort of like, instead of presenting all of the data in a very high dimensional space, you're subsetting the space so each of those images is like a different word that's being fed to the model, except that all the words are being fed at the same time. And so it knows that they're separate words, but that they're somehow related to each other, and it's learning the relationships between them.
Yeah, that's
a reasonable metaphor.
Yeah, that's exactly right. So that it has to be able to see them all at the same time, but also have the ability to know that they are distinct from each other.
So the image T850 would be a very high dimensional vector, and the image U500 would be another very high dimensional vector. Not like 320 like in language models, but whatever the dimension of this image is. Is that sort of making sense, or do they feed it in batches or something like that?
They do feed it in batches, and the tokenization of it is it's only looking at a flattened aspect of it at one time. each
Okay.
one of these is flattened, so it ends up being, I think, just a one-dimensional.
All right, thank you.
And then they have to aggregate, once they do the tokenization of each variable, then they have to aggregate all those variables back together.
Got it.
And they do this with the fine tuning as well. So they can take this model that was trained on a very large data set and fine tune it on variables that were not included in that larger data set.
Ah,
So this actually, in this graphic, they give examples of SO2 and black carbon, but they don't actually show results for those two variables. The results that they show are for surface temperature and precipitation and temperature and precipitation. So one thing that is, they have different they have different training procedures for the climate model, and the results show that the model that has the highest amount of compute ends up being the one that does the best. So I think that this my interpretation of this is that they weren't actually able to get the generalized model that they were looking for, because they would want to get a model that has a smaller amount of compute. Then the other thing is that they were looking for this general model, this Climate X model, to beat the benchmark climate model, and it's not able to do that on all of the variables, especially not all the time. They are able to get better results from the model when it has a much higher resolution. So they looked at different resolutions with I think 5 degrees and 1 degrees, and the higher resolution, the better the model did. So what they end up showing is that the foundation model just still needs a ton of data to work well. So I think that's explained here in this graph pretty well, where if you look at the top row here, the Climate X, and so this is at 5.6 degrees. Climate X, this regular Climate X version has the lowest RMSE as you project out to a 14-day lead time. And this is the model that has seen the most amount of data and has the highest amount of compute. But then they tried these different variations to reduce the amount of compute that the model will see, and it ends up not having as good of a result as you go further, as you extend it further out than the training lead time. So this result is not super favorable for the idea of using a foundation model to get the more efficiency out of smaller data sets. And then similarly, there's a project by NASA and IBM where they used a harmonized Landsat and Sentinel data set, and they created a foundational model based off this data set, where it's going through the supervision process, where it's trying to learn the patterns between the input data itself. So it gets a combination of Landsat and Sentinel, which are two satellite products that measure similar things, but they have different temporal resolutions, spatial resolutions, and durations. So they've created a harmonized data set that has both of those. So they do this so that you can have at any time, if you have a Landsat or a Sentinel image, you can have an image that represents either that can represent both Landsat and Sentinel. So if you have Sentinel, you can predict what Landsat will look like, and if you have Landsat, you can predict what Sentinel will look like. So this project was trained on this data set, and then they tried to fine tune it for a couple of things. One of them was burn scars, but one thing that I know a little bit more about is they tried to fine tune it to predict flood water, so detect where flood water was from any of the Sentinel or Landsat images. They use this data set here, which is from FloodBase Sen1 Floods 11. So they train this foundation model, then they fine tune the foundation model on Sen1 Floods 11, which is a data set that's specifically designed to give you flood delineations. And then they try to predict those flood delineations from those individual images, so either Landsat or Sentinel. So they do report good results, but I was talking to some of my old colleagues at FloodBase that were actually working on this project a little bit, helping out, and they let me know that they're built for purpose models. So flood detection model built just on Landsat or just on Sentinel ends up beating out this fine-tuned foundation model by a lot, by a wide margin.
Wouldn't you expect that?
So this is kind of the big question. Yeah, I think that I would tend to expect that, and I guess like that goes back to the question of why are we seeking out foundation models, and I think that I didn't include that on the slide of why we're seeking this out, but that was proposed as a main motivation in the Climate X paper, and I think that some of the conversations we had at the workshop were kind of about, well, what does it mean if we're spending all this time trying to build these general foundation models, but when you fine tune them, they don't work as well as the built for purpose model. So what does that mean? I don't think it's I think there's other reasons to pursue foundation models for that. And so yeah, I would expect that notion.
Well, I was thinking under what conditions would I expect that? And I would expect that under conditions where the built for purpose model has enough relevant information to solve the task. But there may be situations where you don't have enough relevant information and you haven't thought about where you might get that relevant information. You might not be aware that some other variable might provide relevant information. In that case, I would expect the foundation model to be able to help.
Yeah. So that's kind of like in the conversations we had at the workshop. That's what I think I was trying to get at, is that we aren't necessarily building these to make the best predictions on the data set that we have enough of to train a model on, but what we want to do with it is to be able to analyze the counterfactuals that we just wouldn't be involved in the training set themselves, or use it on a system that we just don't have enough data for, which there are still plenty of those.
I do have a question about Climax, if you don't mind. Before I don't want to prevent you from finishing.
Yeah.
So you gave the example of training on this data set, and then you went to the next one, the fine tuning. And I'm sort of in my head making the analogy that with the first data set, you're learning the patterns of relationships and processes in spatial Earth system data sets in general. You're assuming there are some kinds of relationships which are generic to those kinds of things. And then you're taking it to a specific situation and you're saying that background information about patterns in general could then help because you're starting from a better pre-trained spot and you don't have to do as much work to learn this very specific set of relationships and patterns. But the question I have is, if you go back the previous slide, and I think of each of these images as a word, a different kind of a variable or a process. Is there something about in language, we care about the sequence of these things? I'm assuming here we don't care about the sequence, we just care about the fact that they're presented together. Because one of the things that I would wonder about is if I've got 3 words here, which I'm presenting, and I go to the next image and I've got 3 words, 3 different words that I'm presenting. There's something about the correlation of those 3 words to these 3 words and the relationships between them that somehow the model would be exploiting.
Mm-hmm.
And I'm just curious if there's a whole lot of detail in the background of this that we haven't talked about, or you know, yeah. Anyway, sorry.
I think there is. So the transformer architecture allows the model to see everything all at once. So it's not getting a specific sequence length where after 365 days it doesn't know what happened the year before. So it is seeing everything all at once, and so that sequence information is in there. So these images are one image in a large sequence of events. So it is seeing that sequential context. And one thing that Chris and I were actually talking about on that aspect of the sequence part of it is if you're training a model to predict n lead time forecast, and then you ask it to be fine-tuned to predict n plus m lead time forecast, is that a fair ask? Because I think necessarily there's going to be some degradation, obviously, in performance as you go out further. And what I think that degradation might end up being is the amount of autocorrelation you lose between the sequence. And so I don't know if it's reasonable to even ask a foundation model to be fine-tuned to make a prediction that's further than the specific autocorrelation that might be available to it in the training data set it's seen. So I think that's a huge consideration.
I think Dan has a question.
Yeah, so related to that question, I'm really curious about this tokenization, because I'm thinking of, I watched that, going back to that video that Hoshin shared maybe a couple months ago from, what was it called, Grammarly? And, the way they were talking about tokenization with English, I guess, I just looked it up, there's about 170,000 words. And I'm looking at the size of these, these satellite images, trying to, I can't do the mental math to figure this out on the fly, but, if we're limited to, if transformers are limited in terms of their context length, and the size, the size of the token, I think I'm reading here about, 2048 bytes per token because of the context length, like the conditional probabilities, how far we're going back. I mean, is this actually, are the tokens really the images, or is the tokenization finding the dominant patterns, compressing, the training is finding the dominant patterns in all of these, and the compression is finding, okay, well, these dominant subpatterns within the image, and those are the tokens. And then we do conditional probabilities on like these, kind of patterns that occur within images over time, because it just seems way too big. Does that not? Like these images and the images in sequence just seems way too big for what we're talking about with 100 billion parameter large language models. Does that make sense at all?
Yeah, I guess I don't know enough about the specific details to really weigh in on that thoughtfully.
Before we move on, just a suggestion, Leela, given the tremendous interest in this, maybe we could get one of these people to give a talk about the CLIMAX model. That would be definitely very interesting, I think, for everybody here.
Sounds good.
Thanks, John.
So yeah, sorry, Dan, I don't have a good answer for you there, but that's a good question to think about. So I think that with these two examples, the basic results that I've seen are not like they're definitely not. There's a lot of work to be done, I think, to go to the point where we have something that is a good, solid, like breakthrough in foundation model for Earth system science. So I'm gonna move on from these two examples. And I'm gonna talk about just something that I've been thinking about for over a year now, and I've talked with several of you about it already. But that's I think one of the hard things about the foundational model approaches that we just saw, those two examples, is that the heterogeneity of the data set. So there's so many different types of data, and getting them into the same type of model is a really tough ask. The data might not be corresponding in time, in space, and so there's not an obvious way, to me at least, to train a general purpose foundation model from large amounts of data that might come from so many different places, so many different time periods. And specifically, if you think about the tasks that you want to use it for, where we don't have the data necessary to train a built for purpose model, like water quality, or even, you know, the flooding example is a little underwhelming from what I heard from my colleagues that looked really into it thoroughly. But the problem of predicting flood inundation is still really important, and it's I think there's a lot of work to be done there as well. And this would also be the same for water quality. But I just want to bring this idea up, is that there is a data format that's relatively consistent throughout almost every situation that we ever deal with, and that's just text data. And so there's ChatGPT and many other large language models that are trained on the entire internet of data, or of text. And I got these two examples from the internet. And on the left here is a weather report from 1995 over Santa Barbara, and it has just text. And on the right here is a flood report from Santa Barbara in 1995. This is just one page out of like a 30-page report that also has text that describes a flooding event in Santa Barbara. So you have, on the left, you have what you would want to have as the input to your model. Let's say if this was a forecast on the left here, and what you really want to know is where in Santa Barbara it's going to flood based off of your forecast. I don't see why a large language model wouldn't be a reasonable approach to this, given that we usually convert all of our data into text anyway, especially when we're issuing things like forecasts or alerts and asking people to evacuate. We're doing that all through text. And so since we get forecasts from the weather in text, and then we issue reports of events in text, I don't know if it's really necessary to go through the step of processing all like the raster data directly. But of course, the weather report on the left here has a lot of issues in it, and issuing an accurate weather forecast isn't straightforward, and there's still modeling approaches that we want to take advantage of to issue better weather forecasts. But just from purely practical point of view, I do think that we can start relatively quickly just fine-tuning large language models to be more predictive of Earth systems and things that we would want to look for in Earth systems. And the example I gave you about we want to add a subdivision to a small watershed that's relying on groundwater wells. I have done a lot of experimenting, like trying to get a large language model to give you quantitative answers to that, and it's not able to do that at this point. But I think that it might be a quicker path forward to getting like actual practical modeling results from foundation model going through the text-based approach, especially with fine-tuning opportunities for specific purposes like flood warnings or and system design or operations. So actually at the workshop, I was talking with Andrew about this, and he was going through some examples of like, if it rains this much, how do you operate this reservoir? If it rains this much, how do you operate this reservoir? And the answers that it gives you is actually pretty reasonable. So this is another approach that I think a lot of people are thinking about, but this also needs some work. I just wonder if this isn't a quicker path forward to really exploiting the power of foundation models. Okay. So we've talked quite a bit about what if we were going to start a program for foundation modeling in Earth system science, what were we going to do? And was there a question? So we talked about maybe starting a program to either look into foundation modeling, not necessarily build one for ourselves, because they're just so expensive and they require like so much data that it seems like it's something that needs to come through a huge effort. But we did talk a lot about developing a proof of concept that it's even feasible. And the best experiment we came up with is there's a FluxNet data set out of Berkeley that is kind of a good option for this, where we could train a foundation model on FluxNet data, and which has a lot of land surface processes, and then ask the foundation model to be fine-tuned to do things that aren't available in FluxNet data. And what we would want to show is really concrete examples of that self-organization of data through unsupervised learning. And then we would want to, if we were able to show that, figure out ways to scale that up to larger, more usable models. Developing criteria for success there is not a straightforward thing to do, because like, do we ask foundation model to beat a built for purpose model? Or if you have a system where you have small amounts of data, at what point are you comfortable saying the foundation model is the way to go for a system with small amounts of data? And then one thing that we kind of came up with that was really important is that there has to be, I think, a community of there has to be cooperation in this effort. So if a bunch of different groups start developing their own models, these models are just gigantic and they take so long to train, and they take such large amounts of data. And it could be the case that one group gets there first and they develop the foundation model for systems science that is the one that everyone is able to use, that they can fine tune for your own examples, that works well. Kind of like the IBM and NASA project, but something that is able to show a little bit more success. But if the whole community is going to be using these models, then is there a way to have a culture of engagement and contribution from the whole community rather than competition? And then I still think that the biggest obstacle is the heterogeneity aspect of the data sources. So we need to deal with time series, spatial, and text data to really solve this problem. And then there might be ways to distribute the training load, so we don't need such a big computer, but that's a very technical detail that I think is still requires a lot of pure computer science type work. So this is kind of the roadmap for a future program. And yeah, I don't think I have time to get into the aspects of emergent behavior in physical systems and models themselves unless you really want me to. So I'll stop there and maybe we can open it up for the discussion.
First of all, Jonathan, thanks. That was a really very helpful broad overview of how to think about these things. I didn't in particular see any real conflict between the first approach and your text-based approach, in the sense that ultimately the question is what information and how much information does a person need in order to accomplish a particular task. So if you're providing flood warning information to people by iPhone or by telephone landline in some rural location, you're probably not going to provide them with stream flow forecasts to the millimeter. They're going to be some very coarsely resolved. It's going to flood or is not going to flood or is going to be, 1, 2, 3, 4, 5, level, some kind of alert level or something like that. And it has to be tailored to what they're going to be capable of using and would even pay attention to. So if you gave them too much detail, they might just ignore most of it and might not even be terribly useful. So I'm sort of have the metaphor in the background of the first kind of model. The foundation model is kind of like you're doing self-supervised learning where you're trying to compress by learning structures in the data. And the second thing is more like information bottleneck, where you're then trying to squeeze down and say, which is the relevant information do I need for a specific task? So I saw them as being complementary rather than in competition to each other. One might accomplish one task, as you said, the other might accomplish a completely different or a related complementary task.
Yeah, we did talk about at the workshop a little bit about that, like how to get them to do how to have a model that can use spatial time series and text-based data all like cooperatively. And I guess I didn't really. I think it's obvious. I think it's a really possible. I think it's possible, but I can't think of how to do it, like technically, I guess. I think Gray had some ideas about that, but I wasn't really able to follow them.
I guess I have in my mind the metaphor that there's a part of me, my brain, that is processing all this information at the time and is developing some kind of background subconscious understanding of the world to the extent that I'm paying attention. And then at the same time, part of me is learning how to solve specific tasks. And those are not contradictory to each other. They sort of have to go on in parallel to each other, and solving a specific task is probably over time going to be able to take advantage of that general knowledge, hopefully over time, and then some of that specific knowledge is going to get fed back into the general model. But it feels like I've got sort of two things going on, at the very least, maybe more than two.
But Hossein, this subconscious learning that happens in the background, isn't this very context dependent? So in where you grow up and what's your personal history?
Absolutely, but I think that's the whole point behind large language models, is they learn from a very broad context on the internet of many, many people's reflections and experiences. And the reason we get 30 scientists together in a room is because each of us have different backgrounds, and we don't have this one person who encompasses. But maybe tomorrow's AI would learn everything that I need to know, and then what you need. I mean, I'd have a little agent which learns what I know, another agent learns what you know, another agent learns what somebody else knows, and then would function more efficiently as a collaborative to put all of that information together, which for us as scientists takes a very slow process over many, many years, decades of getting together at AGU meetings or reading papers.
But would that entity have the same experience of joy of learning something?
Okay, now you're getting into the metaphysical. I don't see why not, but you have to define what joy means. To me, I could imagine that something which was very complicated suddenly coalesces into a simpler description length of a process, could be akin to a form of joy, you know, sort of discovery.
Well, this is the definition of reinforcement learning. You gotta have the reward. So I guess reward can be associated with the joy. So in some sense, yes, model would be happy to learn.
It depends on the reward, right? I mean, the nice thing about compression is the reward is that the same amount of information now occupies smaller space, and you can bring in more information. So we'd have to come up with our own new definitions of what that means for a machine. Stephen, you didn't say anything about, I'm sorry, not Stephen, Jonathan, you didn't say anything about, okay, this is your sort of summary up to now. I know you'd like to talk a little bit about the emergent stuff. Do we have a sort of an idea of a roadmap, or how should we as a group be thinking about this moving forward? Yeah, what should we do?
One thing that we talked about is applying for this funding for a 2-year working group that would allow us to meet 2 times a year for this kind of project. But I don't think we really could put something concrete enough on the paper to really get a proposal that would be competitive for that. So I guess that means that we kind of just don't know at this point. So I think the hard thing is if you had one, group with, $20 million to spend trying to build something, that might be a quicker way to move forward than a distributed group. And I think it's not quite clear to me how a group made up of smaller entities really moves this forward. So
it sounds like we, as a community, we still have to build the rationale and the explanation to get it to a point where it's convincing enough that a funding agency or a group of reviewers would say, yes, let's throw $20 million at this.
Right, because I don't think there's any clear demonstration that the approach is the right path, at least from what I've seen.
But do you think we're at the stage of going for demonstrations, or we still need to actually develop the hypothesis, the sort of the logic, the structure, or the idea of the approach?
Yeah, I think there needs to be some demonstration that the approach is going to be successful, considering the fact that there might be quicker ways to get to what you want. So if we spent, if we got $20 million in 3 years to develop a foundational model for Earth system science that used all the data we could ever throw at it and could be fine-tuned on smaller data sets, it would take 5 years to spend all that money and to develop everything. And then by that point, is there going to be something that comes out of IBM or Microsoft or Google that is just already doing the task that we set out to do. And I think that that's actually going to, I'm struggling to see how funding agencies are going to handle this with the quick moving progress of machine learning.
Holger's had his hand up a long time.
I was wondering in particular with now do we have to prove that it works or not? I had some major breakthrough in my head, disproving Darwin and things, and my question was then, could I only get to this result because of my limited knowledge? Right? So because of my personal history, because of my personal path, just because of this personal path, I was able to get to this conclusion. If I had known everything that's out there from the beginning, I would not have been able to come to that conclusion. That conclusion might even be wrong, but I think a model that knows everything in the background might not. It might know too much to be creative, let's say. So the other, I mean, that was just a reflection on where I think that there might be a conceptual problem with the foundational models. But in the end, I mean, if you know everything, you can always try to cut out a path, right? And then you can cut out a path randomly and try to make out your own history. So that's always an opportunity you can have.
You can always cut out on the models.
And what I was wondering, there is already kind of there is ChatGPT, which works on the internet scale text data. But can we just use it and throw like all the climate databases data on ChatGPT, and then see what does it do? I mean, to me it sounds like creating a climate foundational model is reinventing ChatGPT. And then this comes with another problem. I mean, ChatGPT is not always right? I can ask ChatGPT about a bridge over a river in a city that doesn't even exist, and it gives me the history of it. This is kind of dangerous then in terms of, I don't know, flood warnings, right? If it just makes things up.
Yeah, I think those are all really good points. And my opinion on the last one is that what's interesting is about, I think that why ChatGPT works so well is that the fact that it's trying to give you the next word in the series that just falls somewhere reasonably in the distribution, whether it's the right word or not, as long as it's somewhere reasonable in that distribution. Like the color of the ocean is blue is a good example. So the color of the ocean is green is a good answer. The color of the ocean is red is sometimes a good answer. And because it can do that, that's why it works. But yeah, I agree. It can give you what they refer to as hallucinations because of that. So I think the weird thing is that the reason that it works so well is also the reason why that's dangerous that you pointed out.
Laura, were you going to ask your question?
No, I didn't have a question, but I had a comment in the proposal idea. Seems like the conversation already deviated to, more of the theoretical part. Just very briefly, Jonathan, there are, if you are targeting $20 million proposal, usually they actually have a different scheme than if you propose an MRI for 200K. That seems to be also a way to go. An instrumentation type of proposal, because if we are going to work with data, we need data infrastructure. And, the type of hypothesis testing, verification type of proposals seem to be more into the lower range. So if you want to send it to hydrology and they already have a budget, and from the theoretical perspective, it may be between 500 and 1 million. Now, if you look at 20 million proposals, there is a workshop that NSF has. It's called Make the Leap to Large. And right now, I know maybe Hernan knows more about this type of proposal. It's an AI center proposal. And what you actually need to look at is the teams or people from diverse background can collaborate together, and as well as having collaborators from that are not academic. So people like Microsoft, IBM are the ones that seems to be more appropriate to big scale proposals, and really the outreach. So yeah, just think about, just do not bail, I will say, before giving it a try, because you need to just put the bait in the water in order to catch a fish and go from there.
Yeah, we weren't going to try and propose for $20 million. We were going to try and propose for, I think it was a couple $100,000 for that working group, just to see if we can get together and design some experiments to show small stepping stones of the feasibility before, someone wanted to go for that $20 million approach. But that number just, I think, is, if you wanted to build like the complete working final foundation model, $20 million might work. But yeah, we weren't going to go there. We were going to go for this like little steps down.
I agree. I agree. You want to go little steps, and it may be that you're not that far away from having enough of an argument to get a working group funded. It's very likely that if you wanted to get an NSF type center, which would be the kind of scale you would want to have a bunch of people build this, that you might want to engage industry partners, Google and others, as partners in something which NSF would then be willing to back, particularly if those partners also came with their own funding and contribution. But before I leave the floor, I wanted to mention this thing about hallucinations. And that is that in principle, I don't see any real problem, in the sense that if I use a generative model to generate a data point, a string, whatever it is, a story, that is being generated from real data at some point, right? And so as a human being, I can generate stories. I'm a generative model. But what I can also do is anchor those and tell you, well, that's real. It's based on real facts. It's tied to a real thing, or no, it's just loosely based on facts and it's an extrapolation. And so if you were to take a probability distribution and you were to generate a point in that probability distribution space, and then you were to ask the question, well, is that real or imagined? To what extent? If you could project that point onto the closest data points that were used to generate that distribution, you could essentially say, in this way, I can tie it to facts, or in this way, it's completely a hallucination. So, I mean, I could imagine that you should be able to ask ChatGPT to give an assessment of, to the extent to which its answer is fact-based and trustworthy, or whether it's a complete imagination and create an image which is just beautiful for its own sake.
And Hoshin, I think in terms of the description length, so you can also ask ChatGPT to improve the text, but leave the same amount of words. So in that sense, you are not allowing the transformer networks to just have these big words in terms of the stamps that it will create, but it will become
Well,
more
was
reliable.
I was thinking about the example that Holger gave of the bridge. You can make up a story about a bridge over a river. And in principle, I would hope that in some version of ChatGPT, it could tell you that that's a story. There's no such real bridge. Or be able to say it's really based on a bridge because, or I think it's based on a bridge because I read, because part of my database that was used to generate the story was taken from reports of a real bridge, right? Something like that.
But is that something that is doable right now?
I don't know.
I don't know if it can recognize itself, have that conscious of its own architectural network.
I was just trying to think of what you might need to have as a property of ChatGPT in order to deal with this issue of hallucination versus reality. Is as human beings, we seem to have some such ability, even though what I think of as a fact is probably still a bit of a hallucination, right? It's a compression of, and sometimes I can remember things as fact that are not real fact. But there does seem to be some attribute to the way that I store information in my brain and access it, which ties to things that I do actually believe to be true versus I know for sure are not.
Yeah, I think that's the prompting aspect of GPT is exactly the issue there. Like there's reports of if you are a victim of a crime and somebody tells you it was a person with a mustache, then you just automatically think it was always a person with a mustache, whether that's true or not. So that you were prompted, and then from there on, you are convinced that the perpetrator has a mustache, even though they didn't. That's I think that might be the same phenomenon that ChatGPT is dealing with.
Guys, just jump in. Don't wait for me to moderate because I'm not really. I'm only moderating because people are not jumping in.
I wanted to just touch on something that Holger said a little while ago about well, it's a sequence of events that in your whole life. And I recently read "Behave" by Robert Sapolsky, who argues that the training that affects your behavior, your decisions and actions, goes back well beyond your lifetime. It goes back to as far back as like whether your ancestors came from hunter-gatherer or like agricultural society. Like it's a really beautiful book going from the instant, like milliseconds before an action, all the way back thousands of years. So in terms of like training a system, this is it just kind of blew my mind as far as, well, okay, well, what are the sort of what's the context length of a human as a machine that has learned, right? It's immense. But for certain things, the precision of the parameters, like your ancient ancestors, might be very, very, very small. But they might have a very small influence. So that's how I kind of framed it within the large language model kind of context.
Or none.
Thank you. Great talk, Jonathan. I appreciate it. The effort and the amount of the power of the synthesis that you had in all the papers you presented. But and I also support you in the idea of exploring an initial proof of concept through the Ameriflux or FluxNet data. I think arguably FluxNet is one of the networks that has more data per unit of time in the world. So it's a great idea to do it. And the other thing I wanted to say is that the idea of the prior knowledge, involving prior knowledge into the prediction, it's perhaps taken from the reinforced learning area, like Holger was saying, or somebody else, where knowing, imagine you have a sampler, you don't know where the sampler will go to take the next sample, right? But if you have an idea where to go to sample, it'll more efficiently go and find the answer. And so perhaps along the idea of testing the different variables of the Ameriflux would be to create a simple model that simplify in less bits the amount of data that you're able to describe the different variables. And there's some very difficult ones to describe. Wind speed is one of those that have a lot of fluctuations and seasonality and trend. But maybe there's other ones that are easier, like soil moisture, which only changes every 1-2 days. And it remains kind of constant. So if you can create something that allows at least to describe the ones that vary less, and show it that you can create a code that can make the prediction in less number of bits, then that's an improvement. But if the wind speed still needs a lot of data and the number of bits you created, it's not helping you, or it helps you just a little bit, I think it's worth showing to show that too. So I do believe that a foundational paper could help your foundational model, at least with simple data from the Ameriflux Tower at the highest possible resolution. So you're not hiding any patterns, you're trying to explain as much as you can. The other thing I wanted to say is that we were talking with people in Microsoft recently here at UTEP, so we can facilitate the talks if you want to talk to through them for any support or anything they want to. They're very interested in these type of questions. We can help you facilitate that if you want to.
Yeah, that's really great. It's a great suggestion. It's good to hear your support for the Ameriflux project, and then I might reach out to you about the Microsoft connections. Thank you.
I think Tim is next. I was going to ask Yang if he wanted to say anything because he's been studying generative models for a while, whether anything jumped to mind, but go ahead, Tim.
Well, I was just going to plug quickly the book I mentioned in the chat, which is Stephen Wolfram's book on ChatGPT. And the relevance, I mean, among the things he talked about is like how ChatGPT is so good at creative writing, but it really struggles with facts. And so they plugged it into Wolfram Alpha, which supplies the facts. And the really just mind-blowing thing about how they do that is that it was almost trivial because both of these systems share a common interface, which is natural language. So anyway, I found it a really interesting and short read that's worth checking out. And a lot of it is probably available as free blog posts.
Is that something you could summarize for us sometime, Timothy? Would that be something you'd be willing to do?
Oh, perhaps. Yeah, let me, yeah, I could probably do that. I'm not the best person to talk about machine learning, but it is a nice little read, and he breaks it down well.
It doesn't have to be about machine learning. It's just about the ideas behind that and how it works and what they did, and maybe some examples. That would be, not all of us can be able to read all of these things that have been posted on the by the way, Jonathan, that's the largest number of things that have been posted as a result of a talk. So it's really stimulated a lot of stuff. Lila.
Yeah, I just want to say I have been a little bit silent because I have been taking notes. So the idea for this and the future sessions is to have like a document where we can share our notes. And so yeah, hopefully we will have that. And I just want to comment on Hernan's point of using the FluxNet. And also, yeah, I think, Jonathan, that is a great idea because it's a lot of data that is out there and it hasn't been used too much. I have been dealing with this kind of problems using Ameriflux data because the dimensionality is so high and everyone wants to eventually scale this up to places where we don't have that data because we cannot have a Flux Tower everywhere. And one of the constraints of using machine learning and other kind of techniques like for finding causality has been that there is a lot of data, but there is no gut feel method that it's been like well tested, or everyone does gut feeling in a different way. And so most of the time FluxNet data, it's not gut feeled at all. And so if you have like this, a model that can overcome the sequentiality, I see this as a really powerful tool to dealing with this.
Yeah, that was kind of one of the main products we were going to propose as like an outcome of that working group is the gap filled FluxNet. So I don't know, we still might be working on that, but just probably not through that ESIIL workshop. We'll see.
Jonathan, would you be willing to continue in the 3 weeks from now, unless Leela has something else already on the books? It seemed like there was a part you didn't get to and you were already prepared to talk about it. Would that make sense?
Yeah, I think so. So actually, speaking of Stephen Wolfram, it's interesting. The next part actually is a lot influenced by this book here. So I read this right before a workshop in Germany. Actually, it kind of I think a lot of things we talked about in Germany are represented in that book, which is a new one from Stephen Wolfram. So he's kind of the heavy hitter here for a while, but the I can follow up with that emergence discussion.
I think that'd be great because we're already on this topic. So yeah.
Okay, it sounds good. Right now we have scheduled Yang for the next session, but if Yang, it's okay of postponing your presentation. That'll be
Yeah, it's okay. I can postpone my presentation.
Sounds good. So
I will be also presenting this as a poster at AGU too. So
great.
Also, that project is also Tad is helping on that. I don't know if you've all met Tad, but I invited him here. I think he'd be a good addition to this group.
Great, excellent. Holger?
That's also has to do with what Laura said about the funding. I think such a foundational model is really a huge thing, and it needs a huge amount of funding and infrastructure, which might there is no way around, I think, than to ask for funding from companies, and then not by make directly use of that. For example, working directly with the people who have already ChatGPT, and then just feed ChatGPT with the climate data.
Mm-hmm.
We don't have to reinvent the wheel. It's already there.
Yeah, I agree with you, and I was going to mention that when you made that comment earlier. Is that's kind of one of the reasons why I had that text based modeling slide, because I think it does the same thing. I think the self-organization of data is right there with text, and I mean, we could also represent all the climate data with ones and zeros, which is essentially text as well. So I wonder if we could just have some simple embedding network that translates those data directly when we need them to text.
Would there be, I don't know, would there be the chance to apply for some funding directly with a large language model, which is already out there? So to make use of the already existing infrastructure instead of reinventing it.
I think that's a really good idea, yeah. And for sure.
Yang.
So yeah, so I have a comment about like the source of the data used. So for large language model, the data was created mostly by human. So they have some like human perception or human knowledge. For the large Earth system model, the data are mostly natural systems. So I mean, the two systems we are hoping to capture to lower their dimension are actually different. They are actually governed by different underlying processes. And so for the natural system, we also need to have a goal. So we like some tasks. So for the model to learn, like for human, it's like to regenerate like sentence people would likely to hear in some text, in some context. So for Earth system, we need to define such questions so we can effectively train the model. That's my comment.
That's a really important consideration, and I do think you're right. But I'll say that like when we use models, we do use them as they would be text generally. It's rare that you are using a model based on the environmental data without the human interface. But yeah, I think you're right. And that's yeah, I was trying to make that point in the heterogeneity of the data sources. That's I see it as the biggest challenge to solve.
Thank
So
you.
we probably have gone way longer than we intended to. But I wanted to mention one thing before we close for today. This is a question broadly, I think, and maybe even particularly for Stephen here and Dan. I've been thinking about descriptions, and it occurs to me that in descriptions are organized sequences of symbols, okay? And in principle, the simplest organized sequence of symbols is a linear sequence where you got one coming after another in some order. And that's how we create our language, words, and so on. They're like sequences of symbols strung together in time or in space. But then we've got pictures, which are sequences of symbols organized in 2 dimensions. You know, they can be binary, black and white. And we've got objects, which are sequences of symbols organized in 3 dimensions. And then by extrapolation, you could do this in higher dimensions. And we're talking about using models that large language models and other things which have been trained based on the assumption of sequences of symbols organized in 1 dimension. You provide them as a string in some order. And the question I have is, what's lost, if anything, when you take something which is organized in 2 dimensions and you reduce it to 1, or 3 dimensions and you reduce it to 2 or 1? Are we, is there something over there which is making the description considerably more difficult, and therefore the ability to extract structure from that string considerably more difficult just by virtue of the fact that we're reducing it? I'm fine with reducing it to binary, but the fact that we're reducing it from what might be 3-dimensional experience or 4-dimensional experience to sort of 1-dimensional. I'm just curious if anybody has thought about that or has any ideas about that.
I think in principle nothing is really lost, but it's just less efficient. So it's kind of changing your prior to a worse prior, because you lose the idea of which things are neighbors, but you can rediscover that by seeing that something repeats. Like if you flatten a matrix to a vector, you get a periodic repetition of neighbors.
Well, we make it less efficient, right? Because we make it harder to extract that description.
It has to learn that again. So you're kind of throwing away some prior information you had. That's my take. So I think it's definitely worth seeing if there's a way to circumvent that and actually feed it in the form like a sequence of maps just as a 3D block. But I don't know enough.
You'd have to learn some kind of embedding which preserves that information rather than loses it and then has to be reconstructed.
Yeah.
Fun.
That's an interesting thought. Maybe what I'm going to say is a bit biased and not that interesting, but actually, even if the input of language models are 1D in sentences, in the basis, they're still transformers. And what makes transformers great at what they do is the attention mechanism, which is converting that 1D to 2D. So maybe the question can be reformulated into, can we just perform a dimension reduction from something to 2 and just forget that text space, which is an interesting thought.
All right, guys, I know Stephen and I and Dan have to go for another meeting. So Jonathan, I really appreciate that. That was, I think we all appreciated that. Was a great introduction, and I think we all want to continue this conversation. So we're looking forward to hearing from you in 3 weeks then. And
All right.
And then also at AGU, at your poster.
Great.
Yeah.
Look forward to it.
Leila, any last words?
Yes, so we have our calendar in the notes, in the chat box. And so there you can see the future sessions are. Thank you so much everyone for volunteering, because I didn't need to run the the shuffle testing on this. And so cool. Let's
Let me just use this as an occasion to also remind people that don't feel like you have to be an expert in a topic to bring it up for discussion, because it's very useful even if you're just reading about it and thinking about it, because then we get to talk about it. Yeah. So Holger.
Leila, may I ask more a technical question? I think there's always a lot of useful information in the chat, and I always try to save the chat before it's closed. But I know that you're recording the session, and this also saves the chat. Is there a way that you could share the chat after the meeting?
Yes, I can add it to the email, and yeah, it'll be there. Sounds
Perfect.
good.
All right, guys, it was great to see you all. Thank you for coming, and thank you again, Leila and Jonathan. We'll talk to you 3 weeks from now.
Thank
Bye.
you, everyone. Bye-bye.